Good evening, everyone. Well, thank you for coming to this event, which is being sponsored by the School of City and Regional Planning. And we are delighted to see all of you here, despite the late hour. And it gives me great pleasure to welcome you to this event. I'm Shubha Guhathakurta. Many of you know me as the director of Center for GIS, but today I have another important identity, and that is being the colleague of Professor Brian Stone, whose work is being recognized today and has been recognized for quite some time. So I'm really basking in his glory right now. Uh, and Let me ask you, how many of you stayed up last night watching the election results come through? So I didn't get to bed till about 2 a.m. And the reason I'm asking that question is because we could not have held this event on a better day. We are at a historic moment after a very long and contentious campaign, and in a campaign where climate change has not featured very prominently, right? None of the candidates were speaking about climate change in any significant way. But we were reminded that this is an important issue for our future when we were hit by Hurricane Sandy. And there were a couple of lessons that we can draw from Hurricane Sandy, and those are critical lessons for today's, which puts a context to today's lecture. The first is that the damage from such events the damage is very high. It's about $20 billion, right? So it's very important to be prepared for these events. And the second lesson that we can draw from this is that we actually have very good knowledge and science to predict where these storms are going to hit. In fact, if you had followed the trajectory and the path of the storm, it was incredibly accurate in terms of where it hit and the path it had taken. So we can actually say with a lot of certainty that our science and our knowledge systems are fairly adequate, and we have renewed faith in what our scientists are telling us about climate change. So let me tell you a little bit about the book, which I happened to read in 2 sittings because it is a real page turner. I don't know how many of you have read this. This is a real page turner. And I gave it to my wife to read, and she read the first couple of chapters. And the way she described it is that it is fast-paced and action-packed. So if you are waiting to get a hold of this book, now is the time, and they have several copies outside. So Professor Stone, many of you know him. He is the director of Urban Climate Lab at Georgia Tech in our School of City and Regional Planning. His program of research is focused on the spatial drivers of urban environmental phenomena with an emphasis on air quality and climate change. He has been supported through funding from the National Institutes of Health, the U.S. Environmental Protection Agency, and the U.S. Centers for Disease Control and Prevention, among other funding institutions. Prior to joining the Georgia Tech faculty, he taught in the Department of Urban and Regional Planning at the University of Wisconsin in Madison. Dr. Stone's work on urbanization and climate change recently has been featured on CNN, National Public Radio, and in print media outlets such as Forbes and USA Today. His degrees are in environmental management and planning from Duke University and from our own school at Georgia Institute of Technology. So without further ado, let me bring Dr. Stone to deliver this important lecture.
Hey, can you guys hear me out there? I know it's hard to hear it over the hum of the audience. My assumption is they haven't called Florida yet, so people are still riveted watching their TVs, waiting for that outcome. Oh, Steve's got an update for us. So the last time I gave a publicly advertised talk in this school, it was immediately followed up by a grilling by my PhD committee. And so there's a lot of anxiety when I come to these events. And so I'm hoping that I don't have to have revisions after this. I'm hoping that I don't have to have significant changes to the book from your questions. But I want to follow up on what Shiba was saying by highlighting the significance of the moment that we're in, not just the political context, not just the political climate, but what's happening physically around us. And we usually are thinking about climate change at the global scale and how global phenomena are driving things around us, but there's another story that's occurring at the local scale, at the scale of cities. And so that's where my focus will be tonight, and that's where my focus is in the book. So I've got, the structure of the book follows loosely this basic structure, focused first on the anomaly of climate change and how that anomaly is different when we talk about the global scale and how it's different when we think about it at the local scale. Then there's a discussion essentially about risk, about whether we are appropriately assigning risk to the magnitude of the threat associated with climate change, and that plays out again both at a global scale and a local scale of cities. And then what the response should be, particularly at the urban scale. So anomaly, something that deviates from what is standard, normal, or expected. This has a very specific meaning in the world of global climate science, and that is illustrated here in terms of the long-term temperature trend for the planet as a whole. And so when we think about temperature trends, we don't just measure this purely in terms of temperature. We think about it in terms of deviations from a long-term average. And so this zero line here, this zero anomaly line, is a long-term baseline against which we measure change. And that's specifically a period of time from the 1950s to the 1980s. So this is average global temperatures over about a 30-year period. And then we're looking at deviations year to year from that long-term trend. And we see this very characteristic increase, and that gives climate scientists heartburn for a number of reasons. It's a pretty significant increase over time, and it's happening in a very compressed time. When we think about climate over many decades and hundreds of years, this is a very quick trend. What I want to highlight about this is it doesn't give us a lot of information that's useful for cities and for people who work in cities and manage them. The reason for that is that this is essentially designed to be a measurement of how rapidly rural areas are warming. Now, it's not advertised that way, but that's the way it plays out. This is based on a large network of land surface weather stations and sea surface weather stations. And most of those weather stations are in urban areas. Not surprisingly, there are useful reasons for having weather stations in cities. And so if we rely on that network without adjusting it, we're going to have a biased sample of climate in urban areas. And we know that urban areas modify their own climates, and I'll be talking about how they do that and why that's important. But to make sure that the urban temperature record isn't influencing the global record excessively, statistical adjustments are made to urban weather station data. And so essentially what we have is a temperature record that's been modified to represent temperature outside of cities. And so if you're a mayor, for example, and you're worried about how rapidly your city is warming and how rapidly it's likely to continue to warm in the future, this would not be a very good proxy for you because cities have been eliminated from the data set. And so again, continuing with this issue of the global climate anomaly, What, of course, is problematic is the extremity of the trend already, where we sit today. So we're already in excess of hundreds of years of temperature data. And then when we project this forward, based on understanding of the global greenhouse effect, rising concentrations of greenhouse gases, the extent to which temperature is rising is pretty dramatic. Even in the lowest scenarios, the most optimistic scenarios, have us increasing globally dramatically over the course of a single lifetime of a child born today. And so that's a very compressed period of time. So there are probably not many skeptics in the audience, but what I want to highlight is if you are not convinced of the way in which the global greenhouse effect is increasing temperatures, I encourage you to do an experiment of your own at home. This is my research assistant. His name is William. I've had him with me for about 7 years. I don't pay him particularly well, but I feed him. And so what William's got here are 2 mason jars. And so both the mason jars have some regular household vinegar in there, about 2 fingers worth of household vinegar. And then in William's left hand, we've added some baking soda. And so it's bubbling away. We put on lids, and we stabbed in some poultry thermometers. And so what's happening here is a simulation of an enhanced greenhouse atmosphere. That chemical reaction between the vinegar and the baking soda is releasing a lot of carbon dioxide into that jar. And so if we take these 2 jars, one which is vinegar and one with the enhanced carbon dioxide in it, and we put it in the sun, you do have to do it during the daytime, what you will find is that after about 10 minutes or so, even though that reaction itself is serving to cool down the mason jar, it's an endothermic reaction, so it doesn't release heat. It actually lowers temperatures inside the mason jar. What you'll find is that the absorption of sunlight traveling through the jar is such that in the enhanced kind of carbon dioxide environment in here, it will raise temperatures. And if you do this experiment 10 times, you will get this outcome exactly 10 times. This is a physical phenomenon that you can demonstrate for yourself in your own backyard. So don't take my word for it. Try it yourself. In cities, we have that particular phenomenon playing out, of course, and then we also have local scale drivers in the form of what we call the urban heat-on effect. And this gives rise to this urban temperature anomaly, which again is the combination of global scale warming with a layer of local scale warming on top. And so what we're interested in, and this is, of course, a familiar city, this is Atlanta, is trying to develop information on how cities are warming independent of the planet as a whole. If we want to have a sense of how rapidly Atlanta is warming over time, we can't just rely on the global scale data. We have to account for these local drivers. For the heat-on, there are 3 of these. The first is just the loss of natural vegetation, usually in the form of deforestation. When we cut down trees, temperatures rise. And they rise even if we don't pave over the environment, even if we don't build houses and emit waste heat. This is certainly happening in places, tropical regions of the world, with the loss of tropical forest. What's happening is we're losing a major source of moisture retention. Trees are reservoirs of moisture. And so that moisture is important because it's used to evaporate water in the form of evaporation and transpiration in green plants. And so that's a natural cooling mechanism through which that solar energy is used to evaporate water. The energy is locked up in the water, transported aloft, and it's only released when we have cloud formation. And so that's a really important conveyor belt for energy that goes from the land surface to the upper atmosphere. And it cools off environment. So when we cut down trees, we lose that natural cooling mechanism. We like to come in the urban context and then pave over that with preferably, and from our perspective, dark materials. So black asphalt, dark roofing shingles, the terracotta, the red terracotta we see here. That further enhances warming in cities because we're absorbing and storing much more solar energy than we were before. If we were using more reflective materials like a white concrete, that would lessen the effect. But this impervious material greatly increases the amount of warming within cities. And then finally, we have waste heat, which just comes from all the vehicles, comes from industry, comes from buildings. Anytime we are combusting fuel, we're releasing a lot of heat energy into the environment. And so these 3 mechanisms account for some significant additional warming in cities. Heat islands range pretty extensively, but we'll say 2 degrees Fahrenheit to 10 to 15 degrees Fahrenheit in excess temperature in the afternoon on a summer day compared to nearby rural areas. So we asked this question in the Urban Climate Lab, are cities warming faster than the planet as a whole? Because these global data sets basically eliminate or remove or statistically adjust cities, there's no long-term temperature record for cities in particular. And so we look at 50 of the largest cities in the US for which we can get continuous data over at least 5 decades. So we're controlling for things like El Nino and other natural cycles, the natural solar cycle that might fluctuate over time. And so in each of these cities, we have a long-term temperature record, one in the city itself, and then 3 around the city in rural areas. And we look at the differences in those trends over time. What we see here is the rural trend for all of these 50 cities from 1961 to 2010. And this trend line mirrors very closely the trend line that we saw for the planet as a whole. And so we see periods of relatively cooling relative to the zero anomaly, this baseline temperature, and then periods of warming that are sustained into more recent decades and exuding an upward trend. And so what we note about this is in these periods of warming, the difference between the zero line here and the curve itself is what we assume is driven by greenhouse gases. These are rural areas, and so the urban heat island effect should not be at play here. We're assuming there's not a lot of land cover change over time that's increasing temperatures. So we assume this is driven by greenhouse gases. Now we can come in and overlay the urban weather trend on this, and this gives us some more useful information. The first is that on average in these cities, they're all hotter, right? So the average temperature is hotter over time. The difference is about 1.5 degrees Fahrenheit. Doesn't sound like a lot, but it actually translates into significant temperatures in the afternoon. And so we know we measure the existence of an urban heat island across these cities. We can also look at what is driving these temperatures. How much of this is the global greenhouse effect, and how much of this is the urban heat island effect? We do this by, again, just looking under the curve. So under the orange curve, this is the global climate effect, and this is in place both in rural areas and it's impacting urban areas. The difference between these two curves is the impact of the urban heat island. And so in all years, as an average, the heat island is contributing more additional heat to cities than global climate changes. In cities, most of the warming we've seen over the last few decades is from local land use change and energy consumption, as opposed to from the global greenhouse effect. And then the urban trend is just increasing more rapidly than the rural trend. So cities are hotter. Most of that heat is from local drivers, and cities are warming up more rapidly than the planet as a whole. And so that tells us, it gives us some useful information if we're concerned about heat in cities, about the relative magnitude and the trends over time. And so we can measure that. And what we're trying to measure is what we call an amplification rate. If the planet as a whole is warming up by about 3.3 degrees Fahrenheit per decade, so that says at historical rates over the last 50 years, the planet's going to warm up by 3 degrees Fahrenheit over 100 years. Now that's a really low number. It's likely to be much higher because greenhouse gases continue to increase over time. But if we look at what's happening in cities, the rural areas for all of our cities, that's what's being shown in these two bars. The rural areas are a really good proxy for the planet as a whole. So they're warming up at about the same rate per decade. And then cities, on average, have an amplification rate of about 50%. The rate of warming per decade is about 50% greater than nearby rural areas. That's for all the cities in our data set. It's important to note that some of these cities, heat islands are not growing. They're pretty stable over time, or they're shrinking. We see this in coastal areas where there's lots of atmospheric mixing, and so the heat is distributed around. And so we see the rural trend and the urban trend is pretty much consistent over time. All these cities are hotter, but they're warming at the same rate over time because of that mixing. And then we also see in just a handful of cases, the rural trend is actually steeper than the urban trend. And we find that typically in Rust Belt towns where there's been very slow economic development or no economic development for a long time, and you're seeing a rebounding of the urban canopy. And that urban tree canopy is actually slowing the rate of urban warming relative to the rate of rural warming. So that's a pretty small number of cities. What we see here are the results for cities with growing heat islands, and so that includes Atlanta. It includes about 72% of the cities in our data set. So for most cities in the U.S., most of the largest cities have an amplification rate that is much larger. It's 100%. And so if the planet as a whole is going to warm by, say, 7 degrees Fahrenheit over the current century, then places like Atlanta, all things holding constant over time, which is what we don't know, are going to warm by maybe 7 or 15 degrees Fahrenheit over the current century. And so that's a significant amount of warming and raises a lot of questions about public health and about urban materials and things of that nature. So we rank all these cities. This isn't the full data set. I think this is 20 or 25 in terms of the magnitude of growth. And so what you're seeing here is the warming in excess of the rural trend. So again, this is per decade. So the planet as a whole is warming by 0.3 degrees per decade. So any city that's right here, let's say Albuquerque, let's say that's about 0.3 degrees, that means Albuquerque is warming at exactly double the rate of the planet. So it's 0.3 degrees on top of the background rate, the global rate. So Louisville is a real outlier. Louisville is warming at a rate of about an additional 16 degrees per century on top of the global rate. And so I've been spending some time there to talk to them about that particular challenge. Phoenix is up there, not surprising, and then Atlanta. So we're number 3. And we're warming at about an additional 6 degrees Fahrenheit over the century, and that's based on historical rates. So these end up being fairly large numbers when we think about heat waves, when we think about the integrity of materials in cities. If we have a high temperature, an average high temperature in July in Atlanta of about, say, 95 degrees, the planet's going to warm up and make that maybe 102, 103 degrees, an average high in, say, the late O's, 2080s, 2090s. Then Atlanta is going to be even higher than that. Atlanta is going to be closer to 110 based on what's happening. So all that, of course, is back of the envelope. But most of the forces that are driving these processes are speeding up, not slowing down. And so this becomes really, over the course of the next couple of decades, a pretty significant challenge in terms of both dealing with public health issues and dealing with the city itself, with the infrastructure. So the heat island effect is the dominant driver of recent warming in large cities. Until these patterns change, heat island mitigation is likely to yield more rapid results in slowing warming in cities, and that's a really important point. I'm going to talk about, in the last section of the presentation, I'm going to talk about various strategies that are focused on greenhouse gas management. If we zero out emissions of greenhouse gases in Atlanta tomorrow, that will not slow down the city's warming ever. Right? So the local greenhouse gases have very little effect on the actual rate at which the city's warming. It's more about the global scale phenomenon. If we zero out global greenhouse emissions tomorrow, it looks like it'll be maybe 1 to 2 to 300 years before the city stops warming. And so if we really are worried about heat in cities, and we're worried about this from a public health perspective, then we really have to be thinking about urban design and land use tools that are focused on the local drivers, the urban heat island effect. Those are essentially useful tools for reducing greenhouse gas emissions, which we have to do, but they're the only tools we have to deal with these local sources of heat. And so that's what we focus on. So risk, exposure to danger, harm, or loss. What are the implications of rising temperatures? The prologue in the book focuses on the European heat wave, which was a really dramatic event in 2003 that impacted 10 to 12 European nations. What we see here are land surface temperatures recorded from a satellite during this period up to about 10 degrees Celsius as an anomaly, so an additional, in some places, 18 degrees of heat. This went on, temperature anomalies went on for that summer for 2 to 3 months, at least 8 weeks. But there was a 2-week period where it was really, really hot. And it translated into pretty significant loss of life. So in Paris, temperatures exceeded 100 degrees on numerous days, and at nighttime you had minimums of about 80 degrees. So that's like 4 or 5 in the morning, it's still 80 degrees. And that's a really significant threat to public health, particularly the low temperatures, the 80 degrees, because we can be exposed and tolerate very high temperatures. A lot of folks live in desert environments, work outside in desert environments. It's the ability to cool down at night and to recover from that heat that is most important to essentially combating heat-related illness. And so when we're exposed to a lot of heat, just like a tree or any green plant, we use moisture, we use perspiration to cool ourselves off. That elevates your heart rate, elevates the circulation of blood in your system, And so if that has to continue for hours and hours and hours, that wears down your system itself. It can raise your core body temperature and result in some significant heat illness. And so in this region of the world, of course, there's not a lot of air conditioning. It's pretty uncommon to find air conditioning in many of these European nations. And so this started to manifest itself in lots of emergency room visits and lots of people dying. And so the highest heat-related fatalities were in the largest cities. There was a network of temperature monitors in 4 French cities that were not there for the heat wave. They were there for another study that measured urban temperatures to be about 50% hotter than rural temperatures. And so staying in an urban environment during an extended heat wave is an extreme risk to you. And this really played out in Europe in an astounding way. And so over the course of the summer, there were these many excess deaths that are simply measured as in excess to previous years. Same time of year, same month, number of deaths. And so over all these countries, what we saw a death toll that exceeded 70,000 people in one summer. And so Italy and France, about 20,000 residents in each of those countries died. That's a pretty astounding number, given how advanced those medical systems are and their emergency response systems. And so these are lots and lots of people dying in a very advanced part of the world from exposure to heat. And so one of the challenges with heat is that we tend to underestimate it as a true threat. And so to demonstrate this, I talk about the books to bodies ratio. This is entirely morbid and entirely kind of academic geeky. But what I'm showing here are death tolls associated with other events. Some are climate events and some are not climate events. And the number of books that have been published about the events since they occurred. So SARS, acute respiratory syndrome, occurred in the same summer, 2003. It killed about 700, 800 people worldwide. It was close to hysteria. It can spread very rapidly, but it ended up not killing as many people as these other events. Written a number of books about that, not personally, but you can find them. Katrina, in 2005, about 1,500 people died in that national nightmare. More than 200 books have been written about Katrina, can be found in the Library of Congress today. 9/11, not a climate event, obviously. About 4,000 people in total died. Almost 500 books have been written about 9/11, and justifiably so. Even the tsunami in Japan just last year, a huge death toll, almost 20,000 people in a very advanced country. You can already find a couple books on that. The European heat wave, of course, dwarfs all of these events in terms of the number of lives lost. Again, in excess of 70,000. I can't find a single book in any language that's been written about this. And so what I conclude from that is that heat is not assessed as a significant risk by society. It's very familiar to us. It's something that we encounter on a fairly regular basis. It is more deadly in this country than any other form of catastrophic weather. On average, it's more deadly than hurricanes, it's more deadly than tornadoes, it's more deadly than earthquakes, it's more deadly than floods, it's more deadly than all of those things combined in the average year in the U.S. And so we really underestimate the threat of heat, and it's the most likely threat to us moving forward in a warming world. And so if we live in cities, that threat is particularly acute because it's being amplified year after year by both a rising greenhouse, global greenhouse, and by the local urban heat effect. So if you're feeling comfortable because you have air conditioning, let me disabuse you of that. In that same summer of 2003, we had the most significant blackout in North American history. 55 million people were left without power. It didn't last very long. It was driven by the heat. There was a mini heat wave in the country, and it was so intense that the high-low power lines through Ohio started to physically sag under the heat and the intensity of the electrical load in those. And they sagged so much they hit some trees and shorted out the entire network in the Northeast and into Canada. And so most people thought of this initially as a party. Once the power goes out and you're in Manhattan, folks cannot refrigerate their food, so restaurants are opened up. Come have some beers while they're still cold. Come have some free food. If you're in my demographic and you've got to get home to the kids, not as much fun, right? You've got to walk home, so the subways aren't running. You had to walk down the stairs. You've got to walk over the Brooklyn Bridge. It's really hot outside. But still, that night, it was largely a party if you stayed in Manhattan. People had fun. It only lasted about 24 to 36 hours for anybody, and so that's the period of time where this could be construed as something that's somewhat exotic. If it extends beyond that, then it's not hard to imagine that this becomes a significant public health problem very quickly. We can't pump gas, so you're not going to drive out of there. You're not going to get on a subway. You're not going to get on a commuter rail line. You're not going to be flying planes when the control towers don't work. You don't have air conditioning. The grocery doesn't have air conditioning. And after a certain period of time, the generators that are pumping the water are going to fail as well, unless you can deliver that fuel. And so you've got a situation with a lot of people in a very dense environment. It's very hot, and you can't deliver basic services to them. Today, in most large cities, we don't have a plan for this. We got very close to, to very low levels of reservoir capacity in Atlanta several years ago. And I brought in the watershed director at that time to one of my classes, and we were pressing him on what the plan was if it didn't rain. You know, as the linear was drawn down day after day, what is the plan? And we finally got from him that there was a plan to truck in water for the metropolitan region. And so that sounds like a plan that is, would be very challenging to service our population with water trucked in. And I can imagine it would be very similar in an environment like Manhattan. This is the environment in which we're in today, and it's an environment where we have converging trends that are not favorable to us. One, we have rising temperatures, we have rising intensity and number of heat waves, as I'll show you in a minute, and then we have a rising incidence of electrical failures. This is data from the early 90s to the late O's, and we see about a tripling in the number of electrical failures, of blackouts of one sort or another. What's driving this is maybe to a small degree weather, more extreme weather and heat. Mostly what's driving this is just demand for energy and our inability to keep up and service that demand over time. And so these are trends that make it quite feasible that we're going to see a concurrence of a significant blackout with extreme heat. We saw something close to that in DC this summer, which is something that city managers really need to be focused on. In addition to public health, other infrastructure problems in cities, buckling rail lines. This was certainly seen in Europe in 2003. Softening tarmac. This is from DC this summer with their heat wave. Buckling roadways. This is in Illinois in 2006. It doesn't require a mathematician to do the back-of-the-envelope calculation on how much we would have to invest to resurface our urban environments to cope with rising temperatures. All these materials are designed to withstand pretty high temperatures, but not for an extended period of time. That's where you start to see the bucklings and the failures. And so the magnitude of the challenge to urban environments is certainly dramatic, particularly if cities are warming at twice the rate of the planet as a whole. So heat waves. Heat waves are every dimension of heat waves we can measure. This is a study that Dan Habib, one of our graduate students here, has taken the lead on. Every characteristic of heat waves in U.S. cities that we can measure over the last several decades is increasing. The frequency of heat waves in cities, decade to decade, the duration, they're getting longer, the intensity, they're getting hotter, and the time to the first heat wave per year, the number of days until the first heat wave, has declined by about 10 days to 2 weeks. So instead of being in July, it's occurring in June. And so these are trends that are driven, again, largely by global and regional scale phenomena, but are accentuated by what's happening in cities. Are some cities more vulnerable than others? We've asked as well. In this study, we look at whether sprawling cities are heating up more rapidly than compact cities. And we ask this question because sprawling cities are seeing significant land cover change. There's lots of deforestation in a sprawling city, and we know that relationship is there. And so we're curious to see whether sprawling cities are actually having more heat wave days per year than compact cities. And so here we have the diameter of the circle is representative of whether it's a highly sprawling city. So the larger diameter circles, we can be proud of our own home, highly sprawling city. Are cities that rank highly on a sprawl index, and the smaller places, smaller circles, this is horrible from my vantage, but Chicago and Providence are places that are more compact. 3 different gradations of the rate at which heat wave days are increasing, the number of additional heat wave days per year over a 5-decade period. So the red and the yellow are places where heat wave days are rising pretty rapidly, and the blue are places where they're not. Visually, you can see some patterns, but it's easier if we look at it just in terms of quartiles. So the most compact cities are seeing an increase in heat wave days, but it's an increase that's maybe about a third, a little bit less than a third of the rate of the most sprawling cities. And now we might note that a lot of these sprawling cities are in southern latitudes. They're in the southeastern U.S. or out in the west. We can see that here. What's important about the way we measure heat wave days, extreme heat events, is that they are adjusted for thresholds that are region specific. So what constitutes a heat wave day in Atlanta is a much higher temperature than what constitutes a heat wave day in Minneapolis. Those thresholds are based on when we start to see emergency room visits for heat. And so they're directly adjusted to the populations and how acclimated the populations are to various heat levels. And so sprawling cities tend to be associated with more rapid rates of warming and heat waves than compact cities. We believe this is because of the rate of natural land cover loss, so tree canopy loss. We see that for at least one decade in the study. This is the only decade where we have consistent data. We can look at it, but a rather similar trend, with the most sprawling cities are seeing much more deforestation over time than the most compact cities. So cities are confronting some significant warming challenges. They're very much near-term challenges. They're occurring right now. We don't expect it to get much better moving forward. So what will the response be to these challenges? I think much like at the global scale, the local scale response has been somewhat wanting. And so this is a recent advertisement that tries to make a point about our perceptions of risk and how that's not directly in proportion with the magnitude of the risks that we're confronting with respect to climate change. I think there are potentially a number of reasons for this. One of the reasons that's addressed in the book is that we have largely defaulted our local scale responses to the global climate policy framework. And so I want to talk a little bit about that without getting too much into the weeds of the global scale response structure. But it's based on the United Nations Framework Convention on Climate Change is the first policy mechanism, and we build on that with a series of protocols like the Kyoto Protocol. I won't go into all that, but I just want to demonstrate that there's some disagreement on the basic definition of what climate change is. And so we see the definition we use for global climate policy is this: a change of climate which is attributed directly or indirectly to human activity that alters the composition of the global atmosphere, and which is in addition to natural climate variability observed over comparable time periods. This phrase I've highlighted here, composition of the global atmosphere, suggests that climate change is only driven by rising concentrations of greenhouse gases. Now that actually is scientifically incomplete. We know that to be true at the scale of cities. We know that to be true at the scale of the planet as a whole. We'll talk about that for a minute. The global greenhouse effect is driven by two basic mechanisms. This is probably familiar to you, but we'll do our little science class here for a minute. So greenhouse gases accumulate in the atmosphere. Short-wave radiation from the sun is emitted, travels right through the greenhouse gases, is absorbed by the land surface, re-emitted as long-wave radiation. And that long-wave radiation is trapped by the greenhouse gases. It warms the Earth. Perfectly natural mechanism without which we wouldn't be here. The planet wouldn't be habitable. We are increasing concentrations of greenhouse gases, and that's increasing the global greenhouse effect. What we are overlooking with this particular definition is that if you hold greenhouse gases constant and you increase the amount of long-wave radiation that's leaving the planet, that also increases the greenhouse effect. And so cities are seeing an increase in long-wave radiation and sensible heat that is not captured by this particular definition at all. And so by kind of globalizing the climate change problem and understanding it only in global terms, we're missing the major drivers of climate change at the urban scale. And that's incredibly unhelpful. It leads to a response framework that's based on a dichotomy between mitigation and adaptation. Mitigation is defined in terms of greenhouse gases because we understand climate change to be occurring because of greenhouse gases alone. And so that leads to strategies like this. We can try to capture carbon out of power plants and then somehow retain that over long periods of time, and that will reduce the global greenhouse effect, and it likely would if it becomes more technologically viable. The flip side of this is adaptation, which is about responding to the amount of climate change that we can't mitigate. And so mitigation precedes adaptation. Where mitigation fails, adaptation kicks in. I'm not in real estate. I would not invest in that property. That looks like something that I'd be skeptical about. So this issue of an incomplete definition plays out in cities in important ways. This is a picture of Chicago during a 1995 heat wave event. Cities can be conceptualized as large engines for greenhouse gases. We estimate that 70% or greater of all global greenhouse emissions are emitted in urban environments. And so understanding how urban environments contribute to that is important and a key area of research. What we don't focus on enough is that cities are also very large engines for the emission of sensible heat and long-wave radiation. And if we understand climate change to only be driven by greenhouse gases, we're missing the increase in long-wave radiation and sensible heat that is also driving climate change, particularly at the urban scale. And so one of the complicating factors here is that it provides the global framework. When we impose it on a city, it doesn't necessarily incentivize the most productive actions. We know tree planting in cities is an effective strategy to cool them down. If we're focused on mitigation alone, tree planting in cities will sequester carbon out of the atmosphere and ultimately address that problem, but only in a very trivial amount. Tree planting in cities is not going to be a major engine for removing carbon dioxide from the atmosphere. And so if we're focused on the global framework, we're told that tree planting is probably not as productive as something like greater insulation in buildings or driving our cars less or having a more efficient car. Those are all good things to do, but very few of those things will actually cool down the city. And so if you want to cool down the city, tree planting is exactly what you should be doing. But there's very little in the global framework for managing climate change that tells you to do that. And so there's a real disconnect in the terms of the way we understand these things. So what I present in the book or argue from the book is the idea that we should be integrating these two orientations rather than separating them in the form of adaptive mitigation, which I define as climate management activities designed to reduce the global greenhouse effect while producing regional climate-related benefits in the form of heat management, flood management, enhanced agricultural resilience, and other adaptive benefits. The basic argument here is that if we have two strategies that we can pursue to reduce carbon dioxide emissions or their concentrations in the atmosphere, let's say we can spend $50 million on a power plant to reduce carbon dioxide emissions by X number of units. If we take that $50 million and invest it in greening strategies in cities that directly cool down the air, reduce temperatures in buildings, reduce the amount of energy we consume to cool those buildings, could we possibly reduce the same units of carbon dioxide from the atmosphere, but achieve all these secondary benefits? This approach gives us no co-benefits for our local environments. This approach cools down cities while it reduces carbon dioxide. So the argument here is that we should be thinking at the global scale about how to incentivize mitigation activities that also have adaptive benefits. And those adaptive benefits could be in heat management, they could be in agricultural resilience, all the things you see here, flood management. All these things are very closely associated with the types of strategies in cities that tend to cool them down. Our framework today is rather stupid in that it does not prioritize at all or recognize any secondary adaptive benefits of mitigation strategies. So what would these adaptive mitigation strategies look like? The first class of strategies are called sunscreening. We call them sunscreening strategies. This is a graphic from Jason Vargo, just defended his dissertation a few days ago successfully. He's quite skilled in developing effective graphics, in my opinion. This is a neighborhood from Chicago, two neighborhoods that clearly demonstrate the relationship between the basic street scale design and surface temperature. And so in this neighborhood, what he's calling the hot neighborhood, has roughly the same number of houses as the cool neighborhood, 39 to 35, but many different, a much greater number of ancillary buildings like garages. Here it ends up being 71 buildings versus 57. We can see just visually that the tree canopy is less dense than we see in the cool neighborhood. And so by just the physical design of these two neighborhoods, which are very close in space in Chicago, we get a greatly reduced temperature here, a difference of 7 degrees Celsius. So that's a significant difference in surface temperatures that will also translate into air temperatures. Sunscreening are the most basic strategies for dealing with heat island management. Just like the sunscreen you put on your skin. They block out the sun, or they deal with heat that's in cities in one way or another. Planting trees shades the environment, it promotes evapotranspiration, and cools off cities. White roofing does that very effectively as well. An example from Florida, I believe. In combination, these kinds of strategies, these sunscreening strategies, can be very effective in cooling down cities. This is a result of a study that looked at Los Angeles, the Los Angeles basin, and it was asking this question: if we planted trees in all the spaces that are available to plant trees around Los Angeles, and if we converted all the flat roofs, all the industrial buildings to reflective roofing in Los Angeles, how much could we reduce the heat island effect? And what they found is planting those trees, which ended up being 11 million trees. That's a lot of trees. They didn't do that. They did it in a computer, which is easier and more cost effective. When they did that, they cut the heat island in more than in half. They reduced it by about 60%. And so a dramatic reduction as far as the simulation was concerned. And then when they added in the cool roofs, they fully eliminated the urban heat island effect. And so this is a powerful example of one way cities can deal with climate change moving forward. And that is, we can focus all our energies on reducing greenhouse gas emissions, which we need to do, but will lead to absolutely no reduction in local temperatures. Absolutely no reduction, even if we do it globally, which is discouraging, but unfortunately that's what the physics tells us. Or we can also invest in these local scale strategies that have two sets of benefits. They cool down the city. As they cool down the city, they reduce the public health risks, they reduce the stress on materials, they also reduce our consumption of energy, which reduces greenhouse gas emissions. This is a locally oriented strategy that has global benefits as well. There are very few incentives out there to pursue these things today. Green belting. This is a class of strategies that are focused on what's happening outside the city center, just beyond the urban core. We can't just focus on the core itself. The temperatures we see downtown are a product of the region as a whole. Most of the tree canopy that's being lost in metro regions is happening outside of the downtown district. And so Atlanta lost almost 50%, about 48% of its heavy tree canopy over a 20-year period between the 70s and the 90s, which certainly is a period of rapid suburbanization in Atlanta. That has had a significant impact on temperatures, not only in those suburban areas, but downtown. A lot of heat energy is imported downtown. And so we ask the question whether, if we manipulate or if we change land cover in the suburban zone, does that have benefits for not only the suburban zone but the urban zone as well? And so we model this in Atlanta, and we do this with folks over in civil and environmental engineering who run some of the models for us. And so we looked at kind of both ends of the continuum. If we fully reforested the suburban zone, what would that do to temperatures? And if we made the suburban zone fully impervious, what would that do to temperatures? What's important here is that what's happening outside of the city is impacting the intensity of heat within the city itself. And so just focusing on the urban core is not enough. We need to be thinking more broadly than that. And then finally, a class of strategies we call carbon cooling, which are just strategies that are based on that are designed to improve energy efficiency, just like we would in terms of managing greenhouse gases. And so the literature on heat islands suggests that waste heat is a significant driver. It tends to be, out of the three major drivers, it tends to be the least significant, but it still accounts for maybe 20-25% of all the heat in cities is a product of vehicles, buildings, and energy, and even just human metabolism. Even just breathing and living is about 5% in some of these cities. And so that suggests that by investing in kind of classic planning strategies like transit systems, we can actually both offset greenhouse gas emissions and reduce local temperatures if it's done sufficiently, if it's done in an extensive way. So with all that, I want to conclude and note a few final points. Big Bird had a good night last night. I don't make any assumptions about who you supported last night, but Big Bird's happy with the outcome for obvious reasons. Planting trees in cities is something that we need to do in a very aggressive way, but something we need to do with our eyes open. There are costs associated with this. There are the costs of the trees, there are the costs of the management, there are the costs of the houses that the trees fall on when the storms come. This will prove to be one of the most effective and one of the limited things we can do to actually offset temperatures over the next decade or two. And so I think cities will pursue this rather aggressively. But this needs to be done in a way that's not naive. Planting millions of trees will be a huge, huge challenge for cities in many ways, and also will do very little to address these consequent problems that are associated with other aspects of climate change that we haven't talked about, like we just saw with Hurricane Sandy. And so we need to be thinking about the integration of these two strategies, and I think focusing on these local scale strategies is effective in addressing the global scale issues because it much more effectively contextualizes the climate change problem than talking about the global commons, talking about the North Pole, talking about polar bears, talking about 2100. And so the idea that you might be able to argue that riding your bike to work rather than driving is a useful thing to do, not only because it reduces greenhouse gas emissions, but because it will cool down your city if it's integrated with parks planning, and it contributes to less exhaust from vehicles, might be an easier sell. If you see the benefits in your own context of your own environment, that might be a much easier sell. The idea that we should be eating food that's locally grown may become more appealing if we can present this as a way to interact with your own community, as a way to grow the food in your own backyard, even if you're in a highly urbanized environment. This has benefits for the planet as a whole, in that it reduces greenhouse emissions that are associated with food production. It has benefits locally in that it cools down your local neighborhood. If you can demonstrate those benefits to people that are contextualized in the own time scale of their lives and the environment in which they live, it's likely to be much more powerful than kind of an academic argument about greenhouse gases in the future. If you can insulate buildings in a way that creates a space for gathering, that creates an environment that is aesthetically pleasing, that is a very good strategy to not only reduce greenhouse gas emissions, but also reduce local temperatures. And so all of this are strategies to contextualize the problem of climate change in a way that our current policy structures don't do very well at all. And so I often reference the Beltline as a fabulous climate project. It wasn't designed to reduce or address climate change in many direct respects at all. But the fact that it leads to greater green space development in the city, that we hope it will ultimately lead to transit, and that it brings people outside to participate in it and to directly interact with this kind of project is highly beneficial and directly relevant to cities. With that, I will conclude and take any questions that you might have. Thank you. Shiva, I don't know if you want to pass that.
We have two microphones, one over there and one with me.
Hi, I'm Laura Furman. I work as a planner for DeKalb County.
Great, thanks.
And I have two main questions.
Sure.
The first question is, do you have any opinions about tree ordinances and whether or not they're effective? And I guess there's some variation in tree ordinances.
Sure.
But, I know a lot of arborists who say they don't really save trees, but you know, because you have the replacement provisions. But do you think that they're effective in cooling down cities at all? And then the other main question is, I'm a little bit confused because I thought at one point you said that tree planting was not effective to reverse or stop global climate change, but then you went on to say that it does have these regional co-benefits and is very important for cooling down cities. But if it cools down the cities, wouldn't it have some effect on global climate?
It will. It will. It's just the observation there, and I'll get to your tree ordinance question. It's not that it's not effective as a tool to remove carbon dioxide from the atmosphere. It's going to have a very small effect in cities. And so if your choice is, as a city, I want to address global concentrations of greenhouse gases, I can invest in retrofitting buildings with higher insulation, or I can invest in tree planting. You're probably going to choose to retrofit the buildings because the way the global policy structure is designed is that it doesn't recognize these co-benefits. It places no values on strategies that actually cool down local environments. And so there's a disconnect between the local phenomena of warming, which tends to be the principal driver of warming in cities, and the global policy structure that is focused on greenhouse gases alone. None of that is to say we shouldn't be totally concerned about greenhouse gases and actively pursuing it. It's just an observation that we could structure that policy framework to more effectively incentivize actions that have both local and global benefits.
So what's the local groups, what do they say are valuable for removing carbon?
So there are two ways we can deal with atmospheric carbon. One, we can reduce or limit emissions. And so what we're worried about are continually rising levels of atmospheric carbon dioxide and other greenhouse gases. So we can reduce emissions, that's one way to get at it, or we can pull emissions out of the atmosphere. Pulling emissions out of the atmosphere is something that we can do with vegetation and forest management policies. It's something that we hope we can do through mechanical systems, and there's some prototypes in place to do that. Of course, that uses energy itself, so that complicates it. But the principal thrust of that policy regime is on reducing emissions. And it's been fantastically unsuccessful. What was envisioned through the Kyoto Protocol, the principal strategy, has really, as we look at it today, has been remarkably unsuccessful. And so my concern with that is not that we shouldn't be focused on that, is that I think that we haven't contextualized the problem of climate change in a way that has buy-in from communities that would lead to much more effective reduction of greenhouse gases. If we can link this to the local benefits, I think that's a mechanism to get people more active and to changing their behaviors. Let me address your tree ordinance question. Tree ordinances, in theory, can be very powerful mechanisms for protecting existing canopy. They're not designed to increase canopy. And so they are, by design, kind of a defensive policy. And they are constantly under attack. And so in Atlanta, we have one of the most proactive, aggressive standards you'll find in the country, which is no net tree loss. We're losing trees rapidly. And so much of that becomes an issue of enforcement. Some of that becomes an issue of loopholes in the tree ordinance, the way it's structured and the way it penalizes you for cutting down trees, and how fees that are raised are used to replant trees, which is problematic in Atlanta. But for the most part, it's a very useful place to look in terms of establishing tree ordinances and strengthening their enforcement, but it's entirely defensive. It's just about where you are as far as your existing canopy. It doesn't address the fact that we need to be dramatically increasing our canopy. And so we're going to need new tools to do that. I hope that answers your question. Those are good questions. Anybody else? Oh, no. Yes, sir.
Now. So you had a diagram that showed rural areas compared to urban areas, and
Yeah.
much of the argument is based on that diagram.
Okay.
And
you want me to go to the diagram?
Sure, why not? You can.
Tell me which one it is. Is it way up here?
Yeah, it's way back.
Okay. Is it
Wait a
the
minute.
trend?
Yes, that.
Okay, yeah.
Okay, and you had, so in this diagram, it's a little clearer in the ones that come after it, and you have the bar charts.
Okay.
Where you're showing the differential? Yeah, the amplification. So one of the things that's striking is, of course, the rural around cities is actually less than the global. So part of that, it could be averaging, but it also could be related to the fact that land, because part of this is driven by the idea that land has not changed around cities.
Right.
And you're assuming that they're fairly constant. And yet, this is a fairly significant period of time in which agriculture has been lost, and in significant places has been lost to forest.
True.
So that there could be some of the same effects that you were talking about in terms of Rust Belt cities could be occurring in the rural areas around cities, which would tend to accentuate the difference more than, in fact, you might if you didn't have that difference. So I'm just wondering if you could comment about that.
So there have been a lot of, so we use these, the network of stations that we use, and these are all domestic, these are all in the U.S., right? So I'm looking at U.S. cities. And this is a large network, and it's the same network, we draw from the same network that NASA uses and other organizations use to do global climate assessments as well. And so they're very concerned about the quality of this network and how things like land cover around the stations have changed over time. There's some assessment of that, but it's going to be in a very limited area, right? So maybe a mile radius around it. I mean, there are a very large number of stations out there. To be included in this network, you have to pass a rigorous set of tests on, have you had the same thermometer technology over time? Has the station moved over time? Has the land cover changed around the station at time? And so that's recorded to some degree in the metadata for the stations, but it's pretty loose over time. And so could you have areas where you're seeing significant rural land cover change? Absolutely. And I assume that that's happening. One of the reasons we look at 50 cities over 50 years is that we would hope those effects would balance out a little bit. So we see lots of reforestation in the southeast, but we don't necessarily see that in other parts of the country. It just depends on where you are. And so in some places, you're seeing a transition from irrigated agriculture to drylands agriculture. And so there are lots of things happening in the rural areas that will be impacting this rural baseline. We're hoping that it's not a consistent bias. The fact that this is, it's less than the global number, but not dramatically so, gives me confidence that this is a pretty good baseline for what's happening globally as well. And so, does it potentially change the extent of implication? I think it does to some degree, but I don't think it's dramatic. And I think that we look at a large number of cities and a large number of years to account for that. I think it's the best we can do. Does that answer your question? Okay. Yes, ma'am.
So I'm thinking about the Chicago diagram of neighborhoods from Jason's dissertation work, and I'm interested in understanding how to prioritize tree planting. So we saw the density of trees in one neighborhood versus the other.
Yeah.
And I'm sure that, that benchmark of density differs as you move from the southeast to the northwest.
Sure.
And so I'm wondering if you can comment on that, as well as the species of trees that are important from one region to the other.
Right. So this is a really important question, and I think this is where the fact that we've been focused so intently, if we're focused at all on climate change at the global scale, is catching up with us, because there's very little work that's focused on, first, how the species mix needs to change in cities. And so we know the hardiness zones are already changing, the maps are moving. And so trees that are indigenous to one region, say Atlanta, we have maples, we have oaks, we have poplars. These trees, particularly within the city, as the climate is changing locally, are not going to fare very well over the coming decades. And so we need to be replanting, and we need to be thinking about planting different species of trees. Now, what species of trees to plant? I don't know. I really would like somebody to do that study, but we're not doing it, and we need to be doing it city by city, and no one is doing this. And so that's a huge problem. The other huge problem is that we're going to need to be planting tens of thousands and millions of trees at the very moment where many regions of the country are losing the rainfall to support it, and probably all regions of the country are going to be experiencing more intense weather, and so trees are going to be falling on people's houses. And so how do you negotiate those two issues? I mean, that leads me to conclude that the species mix needs to not be the large canopy species in all areas, as it has been historically in a place like Atlanta, but that's just off the cuff. I mean, this conversation is not being had to the extent that it needs to be had. I'll be meeting with the space planning folks for the Institute next week to talk about this. They are planting lots of trees for the campus. They are planting species that are unlikely to be very viable. And so somebody needs to be thinking about this now. I can't answer your question in a satisfying way. Nobody's doing it to my knowledge. But they're great, great questions, because we're going to spend a lot of money on this. So I wish I had a better answer. Steve, are you waiting to ask?
Yeah, just on. This is a new and kind of interesting take on climate change that I think has a lot of a benefit to it, and it's not something I've really thought about before. The traditional things we hear about climate change is more intense weather events, more flooding, more tropical storms, more intense hurricanes, and more droughts.
Right.
And so, and the mitigation techniques that you're talking about here really probably don't apply as much. So what kind of a framework would you think about to prioritize investments across all those different types of risk?
So in terms of minimizing the likelihood, or in terms of adapting to them? Adapting them. Okay. So, part of what I think is valuable about an orientation to urban climate change in its particular permutation, which is largely in the form of heat and extreme heat, is that it is more likely to make people aware of the phenomenon. I mean, what we have today in this country is a lack of awareness and a lack of concern. And so that's the biggest problem, whether you're trying to mitigate or adapt to these issues. And so, you know, my belief is as we contextualize this problem, people will become more active and think about these other issues. How do we adapt to things like sea level rise? I mean, I don't think there's an analog to, I certainly don't consider this approach to be effective in dealing with those issues. So I don't see this as a comprehensive approach to the full range of effects that are associated with climate change. I see these as strategies that are tailored to the principal health-related threat, which appears to be heat. Now, there are probably synergies there. There's lots of wetlands restoration and things we can do as kind of green infrastructure strategies to manage sea level rise and things like that. But there's no way of getting around the fact that we're going to have to engineer hard infrastructure to deal with some of those issues, and we're going to have to abandon areas. But that doesn't come from me. That's just the broader literature. So it doesn't give you a very good answer to your question. I just don't know the answer. Yes, ma'am.
Thank you, Brian. I think so many really interesting co-benefits that only sort of this is starting to get at. But my question is actually very much relative to this slide in particular. And have you found, or is there work being done on the threshold of the benefits of the tipping point, kind of where the benefits of just how compact and dense, and so there's not a, you know, this is the hot neighborhood, the cool neighborhood is actually, you know, has less buildings, has less coverage, it's able to have more trees, but it's also a lot not as compact, it's not housing as many people. So
Right.
obviously there's benefits to the compactness as you
Right.
described, but there's also
Right. Yeah, so nobody knows where the thresholds are. So a lot of my work has been focused on at the metropolitan scale, is it actually beneficial to sprawl, right? Is it beneficial to spread out because you get all those interstitial green spaces, and one would think that's a good thing. But what we find is, like the carbon footprint, the impervious footprint is much greater. And so, you know, it's not beneficial when we look at it at a region-wide phenomena. If we just isolate a downtown district and look at it, as some studies have done, I think, in an overly simplistic way, we might conclude, yeah, the heat island, we can address that issue by sprawling out. But that's not true when we look at the region as a whole. And so that raises the question of, you know, to what extent do we have too much density? My sense is that increasing density requires increasing mitigation in terms of heat island mitigation that is going to be more resource intensive, but it provides the economic base to do that. And so then you start to think about, well, maybe we can be more aggressive with things like biowalls. Maybe vertical gardens become something that we can actually afford to do. Maybe investing in transit becomes something we can afford to do when we reach that threshold density level that supports it, and we can tie that to heat management. Can I tell you that, you know, taking this density level and then transforming this to a high-rise district is going to reduce temperatures? If all of this becomes a green space and we have high rises in gardens, it's quite possible, but I'm not measuring that, and I don't know of anybody that is. We're just not serious enough about it yet. So I think it's a really good question. I think in theory, I don't believe there's any reason to conclude that density becomes too much, but it could be. I mean, we see it at the building scale in terms of heating and cooling buildings. Once you get to a certain building height, it does become cost prohibitive, or at least in terms of energy, it becomes more prohibitive to heat and cool those higher floors. And so maybe there's an analog to that. I don't know. But I think those are the kind of questions we should be asking. There are not many people thinking about it. So it's a great question. Yes, sir.
Dr. Stone, I have two questions. One's a methodological one about extrapolating changes in regions from single point NOAA measurements at airports. And the policy question is, a lot of the drivers of urban heat island, such as changes in albedo and impervious surface, are very similar to water quality issues. And we're seeing a paradigm shift in stormwater and water quality management. And to what extent do you think that these issues should be paired together and stacked as sort of an ecosystem services value to benefit some of the costs that are going to be related with greater technology, as you mentioned in your last answer?
Well, Tom, let me make sure, I'm not sure I fully understand the second question. So how does this relate to issues of stormwater management?
we're trying to talk about mitigation and
Right.
interstitial green space and temperature in cities, impervious surface, vegetation. Those are also factors that influence water quality and stormwater
Absolutely,
management
yeah.
in cities. So do you know of any policy scenarios such as Philadelphia or Cleveland, places that are taking on comprehensive stormwater management that are also thinking about the heat island benefits that they're going to be taking sort of as a secondary effect of that?
Yeah, I think most cities that are serious about dealing with heat management, and that's a small number, are also serious about stormwater. They're just serious about green infrastructure. So it's not that, they've moved into heat management and realized that now we have a stormwater benefit. It's that they are interested in green infrastructure. And so you can look at the Green Alleys program in Chicago is designed for both of those benefits. It's designed to have pervious paving throughout an extensive network of alleys, which is retaining a lot of moisture in the city and sending that to groundwater. That has benefits for cooling. They're using highly reflective paving in the Green Alleys program. They're fully aware of both of those benefits. So I think it's pretty rare to have a city that is not savvy about one issue and sees the connection to the other. It's just basic green infrastructure. And so I think that's playing out. It's playing out in a growing number of U.S. cities. It's just not, there's not a single U.S. city that I would characterize as having a comprehensive heat management plan. There's not a single city in the U.S. that can answer Nisha's question about the species mix we need to be thinking about looking 10 and 20 years down the road for heat management. And I just think that that's a conversation that all of these cities need to be having because whether we want to or not, I think Atlanta is going to try to plant millions of trees once Atlanta comes to grips with what we're confronting. So we need to be thinking about that now. Your first question was about representing the region from single points in space with weather stations. Yeah, and so that's a great question, and it's a real challenge. I don't know if I'll be able to get up here again. It probably won't matter. But so what we're doing is very consistent to what we do globally. I mean, we have probably a greater density of networks than we have globally, right? So we're representing large regions of the planet with a limited number of observations, and that's just the best we can do. And so the way you try to account for that is, one, include a large number of stations, and include a large number of years. But the number of first-order weather stations that have fully collected data without getting into that is pretty limited. And so in most cities, we're lucky to have 2 MET stations that have reliable data that goes back 50 years. If you had that, that would be impressive. In most cities, you only have 1. And so yes, we use a single temperature measurement for a single city to represent the rate at which the city is warming in that place compared to the rural baseline. And I think it tells us, I think the reliability of that data for a single city is not useful. But the reliability for 50 cities at the average is useful. It's statistically significant, it's useful. But it's flawed. I mean, it's a great question, but I think it does tell us something useful as an average for a large number of cities. Yes, sir.
Okay, so I have 3 questions.
Okay.
First off, what would your recommendation be for a city such as Phoenix, which of course was probably not naturally designed to have trees?
I'll answer that, and you can ask your next one. So absolutely. So Phoenix, we have to do these assessments on a case-by-case basis. And so Phoenix is going to be much more, is going to benefit much more greatly from an albedo enhancement strategy, from cool roofs and things of that nature. Planting trees in a region that can't support it is not going to be a good approach. We will have to ask the question, I don't know if Shuba is going to like to hear this, of whether there are going to be some regions that are not going to be highly viable. If we see an increase in temperatures to the extent that is forecast in 50 or 100 years, I don't know what to do with Phoenix, to tell you the truth. I don't know. I think that you can mitigate with cool roofing, and there are other things you can do. You can bring in vegetation. You can bring in various types of xeriscaping, but I do question how viable an environment that will be, which I think is the reality of where we are.
Okay, and then if you go to the map that shows the sprawl of the different cities, so then I was surprised to see that Los Angeles was not shown to be a more sprawling city.
Right.
So it makes me question, like, how do you define sprawl?
That's a great question. Let me see this. I get this question quite a bit. People are fascinated with Los Angeles. So this is just a sprawl index that's been used in a lot of work. and it's based on various measures of population density, local connectivity. There are basically 4 different spatial metrics that go into this. Los Angeles is a spread out, decentralized region with a huge population. And so because it has a huge population, it ends up being right in the middle of the sprawl index. It is totally decentralized, but if you're in those neighborhoods, it certainly has density. It's just not high-rise density. And so it ends up being in the middle of the sprawl index because it has a huge population. And that's why. It's in the middle of the sprawl index quantitatively. Manhattan's at the top, somewhere like Greensboro, North Carolina is at the bottom, and Los Angeles is right in the middle. Well, it's the most compact. I should reverse that. It's the most compact. So it's at the bottom of a sprawl measure. Yeah, Manhattan is the most compact in the U.S. based on this sprawl metric. It's not on there, I don't think. And I think Greensboro is the least. Okay, you had other questions?
Yes, and just one more. So then, what influenced your selection of cities, considering that that Houston, which appears to be quite a sprawled city, or I don't know if by the definition, but it's not on the map, and I'm not sure if at the top, if in the Northeast it says Houston, I mean that says New York or Hartford.
Yeah, I don't know. This is really bad. The resolution on this is bad. I don't think New York's on this one. This is entirely driven by data availability. And so what we're using is a heat stress. We're using 2 sources of data. We're using a sprawl index, which doesn't have every city in the U.S., and we're using a heat index, which doesn't have every city in the U.S. And so we use the confluence of those 2 data sets. We use the largest cities that we can find, the 50 largest cities for which we have sprawl information and heat index information, and that gives us this data set. So we would love to have New York in here, but we don't have the data for it. So we can't. Was there a third question?
Those were all 3 questions.
Okay.